So today I'm going to start with the promise, talk a little bit about the challenges, talk a little bit about our approach, and then get into some of the applications from some of our leading customers for both of our systems. So when we talk about the promise of metal additive manufacturing, this is well represented on the floor today. You'll see the Industry 4.0 nomenclature used often. In the middle side, we really see this as changing the world around us. Really, we're moving away from the mass manufactured, the Model Ts of the world. You can have any color if you want it, if it's black, to much more customized, much more adaptable future. And really, demonstration pieces like this motorcycle that was printed on a large 4-laser machine, showing the types of kind of common devices that impact us every day that we will start to see change around us. This is really what we see devices of the next several decades starting to look as they take advantage of new levels of complexity that are possible with additive manufacturing, gains in lightweighting and mass customization to meet individual customers and regional needs. This one example here from the plastic world, a BMW Mini offering where they can mass customize a dashboard piece. This is something that has been in development, available from BMW for several years now. When we talk about generative design, the ability to take advantage of the freedom that metal 3D printing gives you, transforming common pieces of metal that have been mass produced the same way for decades into new use cases, taking advantage of the lightweighting and the improved functionality of these parts to drive innovation, to drive growth in existing industries. Of course, another advantage of metal 3D printing is the assembly consolidation. Typically, this is best exemplified by the GE nozzle, but we try and use some other examples to show that it's not just aerospace nozzles that this applies to, that there are many other applications out there where taking advantage of the increased freedom of complexity, you can start to combine assemblies from multiple parts involving multiple pieces, multiple tooling, multiple workers assembling them, consolidating them down to a single print to capture drastic improvements in productivity. As we look at the global supply chain, we really feel like this is something that we expect to see drastic changes from. No longer will we be moving raw materials from low-cost manufacturing countries to be processed and then shipped to other countries for assembly at the final destination, but really moving digital files across countries, taking advantage of the freedom that metal 3D printing gives you and being able to change what you're making from day to day. And of course, avoiding tariffs, avoiding some of the limitations that today's supply chain looks at. And of course, the numbers you see on the screen here are before the trade war, so things, the reasoning or the need behind some of the advantages of 3D printing are even more present than some of the data that's originally reflected here. So when we look at current metal fabrication methods, many of these date to the beginning of the Industrial Revolution or even before then. There's been introduction of robotics, introduction of computers to gain efficiencies, but some of the core challenges of these technologies remain, where we're talking about limited geometries associated with the fact that you need to use a mold or that you need to use a process that cannot take advantage of full three-dimensional freedom. Often dependent on suppliers with long lead times, really adding to the time frame or really dictating the time frame needed to take a new product to market. We see additive manufacturing really disrupting a lot of traditional manufacturing by not necessarily completely replacing it in every regard, but really augmenting it in many others, which you'll see in some of the following coming examples of some of our customers using additive manufacturing to augment existing manufacturing to increase productivity of existing manufacturing methods. So, and really we see, Desktop Metal's focus is on the overall life cycle of product development. There's been a lot of gains made in the prototyping and the early product development phase of the product life cycle through additive manufacturing. But we really see both additional gains from that segment, but going further down the life cycle into that manufacturing run, into that post-manufacturing run, the end part market needed for aftermarket parts. Really, we feel additive manufacturing has only scratched the surface in these later areas and has a lot further to go in the early product development phase as well. So when we look at the challenges of metal 3D printing today, we really see it breaking down into three buckets. The first, which is kind of the focus of today's conversation, the materials. The current dominant metal 3D printing technology, the powder bed laser fusion, is a laser welding process, meaning you have to have materials that are weldable to be used with this process. So while the current providers of this technology have largely focused on aerospace and medical applications with higher end materials, Ti-64, Inconels, other super alloys, we see a lot of untapped demands for much more common materials, for stainless steels, for alloy steels, for tool steels. These are materials that far outweigh in terms of usage and consumption globally any of the materials that today's laser powder bed fusion systems are really focused on, and that's been a hallmark of Desktop Metal, is really focusing on these untapped markets, and really to go after these markets, you really need to have the materials that they're most accustomed to help accelerate the adoption of new technology. Of course, cost, the facilities to deal with laser welding of metal powders are substantial. You need trained labor to use these systems, and you need a lot of mandatory post-processing equipment in order to realize the net shapes that you want from this process. And then finally, the speed. While certain companies like GE can buy the supply of laser powder bed systems they need, bring it internally and scale that to meet their needs for end production, we feel like the current limitations of today's laser powder bed technology, which is really operating at speeds much more built around, much more aimed at the prototyping market, where 1Z, 2Z parts, a handful of parts is all we need. But when you start going into mass manufacturing, if you don't have the budget to go out and buy build an entire factory filled with powder bed metal systems, then another process, another method is really needed. So when we talk about the approach here at Desktop Metal, really our mission is to go after that entire product life cycle. We want to make metal 3D printing accessible for engineering development groups at companies, as well as the mass manufacturing teams and the afterpart market that they are responsible for as well. So we've raised a little under $450 million. We're backed by several institutional investors, as well as a number of our lead customers, and Ford, BMW, Google, for example, are investors in us as well. And we've realized this goal, or we've set ourselves up to achieve this goal with two different product offerings. One is our studio system, which one of our resellers has available on the floor out here. This is the world's first office-friendly 3D printing system. This is really trying to solve the issue of accessibility in terms of safety and upfront cost that we would feel has really limited the adoption or the beginning of that learning journey for metal additive manufacturing by drastically reducing the upfront cost and simplifying the process, making it much safer to get a product in the hands of people that are already using plastic 3D printing today, but can't afford that jump for facilities and upfront cost and training to get into metal. And then on the other side, really creating the first technology in the metal additive manufacturing market that has the type of part cost structure that's really needed to take on or challenge established traditional manufacturing. Most traditional manufacturing methods have had decades to
drive down the cost curve, to set standards, to really build up an ecosystem that is very competitive from a part cost standpoint and very difficult to displace. So really taking a fundamentally different approach, driving towards a system that has the speed and most importantly the part costs that's really needed to displace traditional manufacturing when you start talking about volumes of parts in the tens, hundreds of thousands, or even millions. So Desktop Metal's material story is really at the heart of the founding of the company, when our founding team and our CEO, Rick Fulop, who was an investor in Proto Labs and one of the earlier investigators or adopters of powder bed laser fusion. As he was bringing this technology into Proto Labs, he really felt like a number of the drawbacks that we had just talked about, the cost, the speed, the materials, really were going to prevent this technology from breaking out of the high-end aerospace medical applications where it's commonly found today. So Rick really wanted to go about making more commonly used materials, more widely available used materials as one of the core facets of Desktop Metal, basically not building a whole new process that required an entirely new materials type or supply chain to be developed to support it, but rather tapping into an existing market of metal powder that has been around for decades, has standards established with it, and has a number of use cases already in mass manufacturing through metal injection molding. So in doing so, one of the greatest advantages we have is just the existing material that are available from powder metallurgy producers and suppliers today. So when we looked at what materials did we want to go after, we really focused on, okay, well, what materials are the highest, the most in use across industry today, not just looking at medical and aerospace, but globally. Where do we see materials coming from? We see a lot of stainless steels, a lot of tool steels, a lot of carbon steels as dominating the market in terms of usage, but in the additive manufacturing worlds, they're either not a focus due to the lack of interest from aerospace and medical, or they are just not compatible with the process when you start talking about things like tool steels, which are not weldable through a laser welding process. So tapping into an existing market, leveraging an industry that has had decades to drive competitive pricing down the cost curve, and today is several orders of magnitude larger than the current powder bed metal powder market, and tapping into that existing supply chain, adapting it for our new process, and then driving that to the broader market. So when we look at stainless steels, 17.4 is a great example. In the MIM industry, this is one of the most commonly used steels. It has standards associated with it set by the ASTM board or the MPIF, Metal Powder Federation. And there's a certain level of expectation in the industry already for this material, how it behaves, and what they can expect from it. So by us basically tapping into that supply chain, tapping into these standards that already exist, and now putting them through a new process, we feel like this has been well received by people that are trying to get into metal additive, but aren't interested in the super alloys or the really niche alloys that are most commonly found in the high-end applications of aerospace and medical. So when we look at taking 17.4, another common use case of it is to heat treat it and improve the strength performance of it. And again, this is a process that has a standard associated with it. By leveraging that standard, by testing to that standard, we're able to show customers new to additive that this is a material that they already know, that it's performing the same way that they're used to performing through the traditional manufacturing, and that the post-processing of this material will deliver similar performance to what they're already used to. So when you're asking a customer to transform the way that they're currently making a part to this new additive world, we're already asking them to change slightly, at least, the way that they design the part to take advantage of additive manufacturing. We're asking them to change their process to this new additive process, whether it be the studio or the production system. So having at least one of the cornerstones, the materials, be the same, have it be something that they can latch onto, be familiar with, we have found has been very helpful in driving adoption or accelerating adoption. When we look at our materials, we're trying to kind of slot ourselves in as a MIM alternative. So talking to customers who are currently making their part in press and sinter or casting, or if they're making it, machining it from a wrought alloy, showing them that if they're familiar with MIM, this is a very similar process that we're delivering here, and that the expectation that they've had in their previous usage of MIM can translate directly over, but also helping that education part, telling them what is different, what are the new learnings that are needed to take advantage of this technology, but always basing it on something relatable, not bringing a whole new solution to the table and asking a manufacturer or customer to start from scratch in terms of their adoption. And when we look at a little deeper into the materials, I think one of the biggest questions we get is just especially from those maybe more familiar with plastic, is what kind of isotropic properties are you talking about? How weak are your materials in Z compared to X and Y? And this is where we invest a lot, both internally but also publicly in a lot of the powder metal conferences globally, to show customers that because of the sintering-based approach that we take with metal, that you're going to experience grains that grow across layer lines, and you're going to experience an isotropic part that really is vastly different from anything you've experienced with plastic before. This isn't just trying to weld layers together, but really building a part cold and then heating it up all at the same time through a sintering process really enables this isotropic property to really shine through. Again, a little close-up here showing that even the internal of the part is the same as the external of the part. Another example of
Ladies and gentlemen, the ABB workshop in Hall 2 is about to begin. Kindly proceed there now. Thank you.
Another concern with powder bed laser fusion, where laser welding of thick cross sections versus laser welding of thin cross sections usually results in different microstructure, so much so that usually a required post-processing annealing step is required. Here we're showing, again, because of the fact that we print cold and we sinter everything at the same time, thin cross sections or the edge of a part and the center of a part all come up to temperature at the same time. Those metal powders fuse at the same temperature, and the stresses created through rapid heating and cooling that you experience in laser powder bed just aren't there with this process, which is again, for someone coming from MIM, press and sinter, this is much more the microstructure that they expect to see. So when you're comparing with laser systems, straight off the printer, you can see a very different type of microstructure that's being created. One on the left, when where laser welding layer by layer shows stresses and strains and geometry in the microstructure that is very foreign to the vast majority of the market who've never been introduced to powder bed before. And yes, while you can take this microstructure and transform it to something that looks to the right through post-processing, that's added cost, that's added know-how that the customer is going to have to undertake to get back to the material type of material properties and structure that they're used to. Similarly, on our production machine, you can see the grains here, a little larger, based mostly on the sintering approach that we use. But again, this is uniform microstructure, much more relatable to press and sinter, to MIM, than what most customers will experience with laser powder bed today. So when we start to look at applications, starting first with our studio system, for those who aren't aware of the studio system, it has really drastic upfront cost structure associated with it, different than the laser powder bed. No longer do you need to invest in dedicated facilities, dedicated trained staff, all of the safety requirements that are inherent in dealing with metal powder that you're shooting high-powered lasers into. But this is a cost structure much more akin to professional plastic 3D printers. This is a level of complexity that is much similar to the plastic FDM systems and is able to be installed in a few days in an office environment versus having a dedicated facility built to house this technology. Similarly, while we are a powder-based process and we sinter metal powder, we don't deal on studio with metal powder. Again, a big drawback or differentiator we feel for the current laser-based techniques is just the fact that you're dealing with metal powder has a whole lot of safety and training concerns that come with it. So by adopting this MIM-like material, by taking that metal powder, by binding it with wax and polymer binders, we are able to put it into this rod form that you see here, which can be handled by hand, and whereas something that for aluminum powder, for existence, you would never hold a lighter to aluminum powder unless you were looking to head to the hospital. This rod form, if this was an aluminum rod, for example, you could hold a lighter to this, and there's no effect on the powder since it's completely encapsulated by this binder. So, delivering safer materials that are easier to get a hold of, easier to use, and easier to change as well. So when we look at laser powder bed, particularly in the prototyping market, there's not always constant demand enough for one material to dedicate a printer to one material. So laser powder bed today usually requires, for even the most trained users, a half day to a day or at least a shift turnaround to completely clean your system, put in your new metal powder, recalibrate your system, and get up and running. Versus on the studio system, we package our materials in these easy to exchange cartridges, very similar, to lessons from the 2D worlds that moves to on the laser side, moves to easily to swap out cartridges instead of having to pour their toner into the printer itself. This allows for customers to switch materials easily and take advantage of the flexibility of a prototyping system by changing materials based on your needs. So as we start to look at industries that Desktop Metal is focused on, you're going to see a different type of focus than most of the laser powder bed guys have today. Whereas medical, aerospace are the dominant focus areas, we see a lot of untapped demand coming from basically the entire rest of the manufacturing industry. So these are industries that either laser powder bed doesn't provide the material that they need to accomplish their goals, or the cost complexity of the system is too much for them to take on to put into use in some of these kind of more cost sensitive industries. So when we look at automotive, we start to see components that you'll come up against much more regularly in your everyday life. So although a number of us, I'm sure, fly on planes and maybe have even flown on some planes that have the GE fuel nozzle in them, it's tough to kind of see the impacts that Additive has had on that airline, on that product when it's hidden away in the engine, versus here, you're starting to see mass customizations of gear shifters. You're starting to see brackets and mounts, or maybe some components under the hood that are starting to look a lot different than what you would see today for a car rolling off the line. The great thing about automotive is, these are customers or investors like BMW and Ford. These are companies that have been using powder bed fusion for decades. They've been very successful implementing them on their race team, but even a company like BMW, who owns Rolls-Royce, the current cost structure of laser powder bed just doesn't allow it to make parts, even end-use parts for a production Rolls-Royce vehicle. So this is really that first step in unlocking this pent-up demand, taking these designs that many of these automotive companies already have kind of off the shelf due to their racing teams, and starting to move those into production end-use parts in vehicles that you and I can buy. Consumer products, another example of much more cost-sensitive industries, being able to prototype much more commonly seen components that really start to get 3D printing moved out of the highly specialized high-end applications in biomedical and aerospace, and moved more to the front of mind for consumer, giving them more choice, giving them more flexibility, giving them more ability to mass customize components that they have always wished there was a path forward to deliver on this. Heavy industry and gas, this is a great example of an industry that, again, while being more cost sensitive than aerospace and medical, has a number of materials in the tool steel and in the carbon steel market. These are materials that have been really cultivated by the oil and gas industry, developed, optimized for their use case, and obviously manufactured by traditional manufacturing. Now, with being able to bring an additive solution that's affordable and delivering materials that are the ones that have been optimized for this end case to bear, we start to see a lot more adoption. We start to see these customers really seeing a path forward for additive impacting their industry. Similarly for machinery, again, moving away from tie 6.4 or not focusing as much on Inconel, but delivering on the low alloy steels that tend to dominate the machining industry. Again, showing just a couple of examples of parts that are difficult to make through traditional manufacturing, where the demand is there to move to additive, but there needs to be a cost-effective way to do so. A hallmark of 3D printing on the plastic side has been jigs, fixtures, taking that next step, evolving that from just use cases that where plastic is acceptable from a strength or from a temperature survivability standpoint, moving it to metal, taking on new applications in the jigs and fixtures where strength or heat resistance are really needed to deliver on this. So these are jigs and fixtures that are commonly machined today, typically very complex geometries that require multiple parts to be machined and assembled together. Now, the studio system in particular is well positioned to deliver solutions to these overworked machine shops where jigs and fixtures tend to fall to the bottom of the part queue and often have very long lead times associated with them. Moving to a system that individual teams can control, where they can now forego having to design multi-part assemblies and figure out how to assemble them to just printing the jig and fixture as they need it. And then finally, tooling. This is one of the biggest ones we see for the studio system in particular. So while some companies have been using miraging steel that the powder bed systems can produce to try and adapt to tooling applications, the most common tool steels in the world, A2, D2, H13, P20, S7, these are all materials that have been optimized for their particular use in traditional manufacturing, and not having the thermal stability of H13 or not having the hardness of an A2 or D2 really makes it a much tougher sell to break into that application. So really delivering the material that the customers are used to, a material that traditional manufacturing has already optimized for a given application, and just introducing 3D printing capabilities to enhance the capability or simplify the development of is really where we have seen a lot of demand on the studio side. So this is an example of one of our customers, Master Drilling. This is a company that makes those very large drilling setups that you see there for drilling into the earth for mining applications. So this is a company with a worldwide footprint. Most of their manufacturing is done in China, whereas most of the components are used in places like South Africa, other areas where you would find a lot of mining applications. So this is a planetary sun gear that's at the center of that drill that you just saw on the previous side, 3.5 kilogram part. that is, as you can see, a sizable part that is being put under pretty extreme forces as one of the main parts of the assembly that takes the brunt of the drilling operation. So through 3D printing this part on location, this is now a part that is 60% lighter, which puts less wear and tear on the machine, but it was also produced with 80% shorter lead time, really fundamentally changing the type of setup and planning that this company needs to go through when figuring out how it's going to distribute inventory globally or how it's going to maintain its equipment in some of these remote places. So today, the part is largely made in their factory in China. It's a 3-month lead time for them to receive that part, and that's not including some of the shipping logistics required to get it into some of these remote places. But by basically adapting the studio system, placing that at location where they're doing the drilling, and taking advantage of the fact that this is 17.4 that can be hardened, just like they're hardening the current version that they use, and putting it through successful field tests, as you see here, basically drilling pilot holes. So this is already a part that's been put into use and is currently being used in many of their gears globally today. Another customer example, this is Turner Motorsports. They're considered kind of the leading BMW race team in North America. And this is a group of guys that really are trying to squeeze every ounce of performance out of their vehicles, but does not have the kind of budget associated with a Le Mans company or another racing company that is maybe backed by corporate BMW. So these are guys that don't have access to metal 3D printing today, despite a number of use cases that they would largely benefit from. So this car that you see here is what's at least those in the know effectively refer to as the best M3 that BMW ever made. It's the 2001 M3, which was the last M3 that had mechanical driving, basically, before BMW moved to electronic steering. So while they feel like this is one of the best performing cars in the 20 years since this car was made, BMW has obviously made tremendous gains in terms of the performance of the motors. So the team wants to basically take a current BMW high-performance engine and retrofit it into the 2001 version to take advantage of the what they refer to as improved steering capabilities. So here's a key thing here is that they don't want to modify any of the steering linkages. They don't want to change any of this, what they feel is perfected steering capabilities of this M3. But they need to design an engine mount that's going to replace the current one so that they can fit the engine in there without having to or fit the current engine in there without having to affect any of the steering capabilities. So to do this would normally take the team several weeks to design the requirements for a new mount, to then design the assembly and the manufacturing method for putting this together and bringing that to bear on the race car in time for its next race. So really an entire team all engaged really in just this one upgrade due to the time constraints that they have. But by leveraging some of the other advantages of 3D printing and Industry 4.0 being generative design, they were able to, and this is Live Parts, which is Desktop Metal's version of generative design software. They were able to basically design this in our software and have our generative design tool build it in real time for them. So here you can see the part. This is after the constraints of the bracket have been input into SolidWorks. Again, leveraging a similar story here, leveraging a software install base that is distributed widely, and that there are many customers already very accustomed to using SolidWorks. Our software plugs into SolidWorks and allows you to take advantage of generative design, but staying within the framework that you have already known and been trained on. So this right here was basically a real-time simulation of the bracket being grown in real time based on the constraints that the engineers had put into the software. This is really then almost directly migrated to our software for printing on the studio system. This is our Fabricate software. We do not require Magix or any third-party software to print in our system, but migrating that product from design to printing, and because of the advantages of our own generative design software, knowing how a studio system prints parts, we're able to rapidly iterate and get the design that's needed. Now, this part was larger than the studio system could print in one shot, so what you see here are the two parts that they designed and welded together. Again, because this is a material that they're very familiar with, because it behaves just the same as their cast, as their press and sintered parts, they already know how to use it, they already know how to weld with this, and you can see the welding that they did right here together. So this is the final part. This went into testing, passed all of its testing requirements, and went into the car in time for the racing team. And as our distinguished speaker kind of alluded to in his comments, this is a great example of bringing in new technology and additive and generative, and not necessarily replacing workers, but really augmenting them, enhancing their capability. Whereas this would have taken the entire team focused during the sprint to get this change made by the next race. In this instance, this took one person 3 days to be able to design this part, and then an additional couple of days to print it, freeing up the rest of the team to make additional changes, other enhancements to the car to get it ready for the race that they were preparing for. So really an example of increasing productivity, enhancing the existing workers at Turner Motorsports. And there you can see it installed in the car, by moving or by designing all the keep-out zones, really perfectly fitting in exactly where it needs to hold the engine but not affect any of the steering linkages. Next we have another customer of ours. This is a video, another example of what we see the studio system and eventually production system really delivering new capabilities, new enhancements in productivity to an industry that's been pretty stagnant in terms of the powder metallurgy industry in the U.S. So have a listen.